In this video, I just want to talk quickly about the mechanism for dissolving metal reduction. And dissolving metal reduction, you'll remember, is where you can take an alkyne and then you treat it with sodium metal in liquid ammonia, and what you end up getting is a trans alkene. So you end up adding two hydrogens onto the molecule. The hydrogens ultimately come from the ammonia, but how does that happen? It ends up happening through what's called a radical mechanism, and it'll look unusual, and it's not something you'd have to draw on a test. So again, if you're trying to prioritize things with a very limited amount of time, this video is maybe not for you. But if you're interested in how this stuff works, this is a really interesting topic, and it will help prepare you for the next chapter. Okay, so we're used to thinking of three different phases: solids, liquids, and gases. But actually there's a fourth one, and the fourth one is the most common phase in the entire cosmos. Aside from solid, liquid, and gas, there's a phase called plasma. So if you imagine, a solid is where atoms stick together in a rigid pattern. Liquids are where molecules will stick together, but not in a rigid pattern. They'll sort of brush against each other, roll around each other, but they'll still stick together. Gases is where the molecules don't even stick together, they're bouncing around. And a plasma is where atoms don't even stick together. So a plasma is like a potpourri of electrons, protons, and neutrons that aren't stuck into or organized as atoms. You just have them whacking past each other, brushing against each other, knocking across each other, like pool balls hit in a bunch of chaotic directions. Plasma is the most abundant of all of the phases in the universe because stars are made of plasma. Stars are hot soups of protons, neutrons, and electrons that mostly aren't associated into the shape of atoms. Now what's interesting is that metals can either be considered solids, or you could also consider them as plasmas. It's sort of like this old perception puzzle. You could look at this and see a rabbit. So this is the head of the rabbit. Here are the ears of the rabbit, right? Its mouth would be like right here. So you can do that, or you can look at this and see a duck. Here's the beak of the duck, here's the eye of the duck, the back of his head is right here. So looking at that one image, you could see two things. And it's equally true that it could be a rabbit or a duck. What is it? Well, it's kind of both. It depends on the perspective you want to look at it in. Metals are very much the same thing. You could look at a metal and say that it's a solid. It does have recurring nuclei in a consistent pattern. The nuclei of the metal are repeating over and over again in a certain pattern. But the electrons in the metal are not associated, are not stuck to individual nuclei. They're flying around the entire chunk of the metal, and so you have a subatomic particle, electrons, that's not associated into atoms, and so it starts to act like or sound like a plasma. So you can think of metals not just as solids, but also as plasmas, and that's the reason why they're used in wires. The electrons are able to fly from one end of a solid piece of metal to the other end, and that's because the electrons are not stuck to individual nuclei into individual atoms. So metals can act both as solids or as plasmas. And in this mechanism that we're about to draw, the metal, the sodium, and that's what we have a picture of here, that sodium is going to act as a plasma to give electrons away. Now, you'll notice this is being kept in oil. That's because sodium is so reactive, if it's exposed to air, really, if it's exposed to the water in the air, humidity in the air, it reacts with it. It's a very exothermic reaction, and so you tend to get explosions. So usually when they store it, they store sodium metal in oil. Otherwise, it's an interesting metal. You could cut it with a butter knife. Okay, so the first step here is we need some sort of alkyne. Now, it doesn't matter what the R groups are, we just need the triple bond. So I'm just going to use regular old R groups here. Okay, and the other thing we need is sodium metal. So we have this sodium. Now, really, this sodium is an array of trillions of nuclei, that are all stuck like blueberries in dough of electrons whizzing past them. But to represent that whole situation symbolically, I'm just going to write the symbol Na and an electron that is not especially tied to that metal. It's whirring around the whole thing. And the metal does not have a lot of electricity, so it can easily give this away. Now, I'm going to draw a curved arrow to show how that one electron moves. That one electron can knock into one of these carbons. Now notice the head of the arrow, it only has one hook. It's called a fishhook arrow. That's because I'm only moving one electron. The head of the arrow gives you information about how many electrons you're moving. When one of the electrons slaps into an alkyne, a carbon in an alkyne, it breaks one of these pi bonds. But it breaks it evenly in half, so that one of the electrons goes on one carbon and the other goes on the other. That's called homolytic cleavage. And again, this is going to look like a really weird mechanism because it's something we haven't seen yet, but it's a great precursor. It's a great trailer for the next chapter where we're going to be dealing with these unpaired electrons a lot. Unpaired electrons, by the way, are called radicals. So a radical is an atom that has an unpaired electron, and that's what we're going to get here. So after we do this homolytic cleavage, what we end up with is the two R groups. We still have one pi bond intact. You'll notice this carbon here has 2 electrons on it, so a full lone pair. This one over here, though, has an unpaired electron. So this is a radical, an atom with an unpaired electron. This has a negative charge, and so once you have that, you can bring in the sodium. Remember, the dissolving metal reduction has 2 things. It has sodium metal and ammonia. So once you have this unstable intermediate, you can bring in the ammonia. Ultimately, it's the ammonia that's going to donate the hydrogen. So this full negative charge can steal a hydrogen from ammonia, and the electrons go back onto the nitrogen. This is really unstable. You have a full negative charge on an atom that's not electronegative and that's small. It's because that's so unstable that it's able to steal a hydrogen from ammonia, which is usually thought of as a base. But acidity and basicity are all relative things. Something only acts as a base if it's combined with something that's less basic. So this is more basic, so this ends up acting as the base and steals the hydrogen from ammonia. Ammonia, by the way, notice it's the nitrogen version of water, and it ends up playing a really big role later on in organic chemistry, and especially in biochemistry. Ammonia is the ultimate derivative of amino acids, at least half of them. Okay, so after we do that, we still have a radical. Now we've added a hydrogen on here. So we have that hydrogen there. We still have the pi bond here, but we still have the radical, the unpaired electron on that carbon there. Unpaired electrons are really, really reactive because they're like magnets, just open to space. So this is moving around and it's knocking around in a whole bunch of stuff in a sort of galaxy that is contained in your test tube or beaker. And it knocks into the sodium again, and because it's so unstable, it can stick to one of those. You can move one of those electrons onto that carbon. Notice I'm using a fish-hooked arrow there, just to show that I'm only moving one electron. What you end up with after that step is a full negative charge. A full negative charge. And so, once you have that full negative charge, you just get another molecule of ammonia that comes in. And you do a proton transfer that steals the hydrogen, the electrons in the bond go back on the nitrogen, and you end up with an alkene onto which you've added 2 hydrogens. And the hydrogens are trans, and that largely has to do with this step here. In this step, this double bond is trigonal planar. You have electrons on one, electrons on the other. The most stable way they can be is facing away from each other. And so that forces this double bond to be trans. And then as the electrons are replaced by hydrogens, the hydrogens are trans, and so are the carbon chains. So that's the mechanism for this. Notice what we started with was an alkyne. We mixed it with sodium and ammonia, and we ended up getting a trans alkene. So it is an interesting reaction. It introduces you to the concept of unpaired electrons being very reactive, and the name for that are radicals. And it introduces you to fishhook arrows, And it also introduces you to this really interesting concept that metals, although you think of them often as solids, can also be thought of in a sort of perception game type of way as plasmas, substances where protons, neutrons, and electrons, subatomic particles, move past each other without being associated into atoms. And a fun fact on that is that only 5% of all of the protons, neutrons, and electrons in the cosmos are cold enough to form atoms. So you can get a sense of how significant plasmas are. Plasmas, you have a lot on Earth. First, there are older plasma TVs, but also the aurora borealis is a plasma, where if you've ever had like static electricity make your hair stand up, that was a plasma, right? Electrons that are not associated into atoms. And so you can think of these solid metals as that way, and that gives them this unique behavior.